Thank you very much, and I would like to thanks for letting me speak here. It was a very interesting meeting. The subject of the lecture is slightly off. It's not according to this. There are a couple of words that will be involved in my talk from the title of the workshop, but I hope you find it interesting anyway. So it's a joint work with Jens Karl and Jesse Wolfson. And it's a work in progress because things are not quite written down yet, but computations are done. So it comes out of some previous work that I did with Jens on time symbol in one-dimensional case. We're wondering what happens in high-dimensional case. And we ended up with finding out certain constructions which we didn't think of. So maybe background. Some of main object is to write down a construction invariance of algebraic K-theory. And there is this construction due to Kohn and Karoubi. It's called the multiplicative Chern character. It goes roughly like this. So think of an algebra. It's algebraic K-theory. And there is a map from its algebraic K-theory to, well, cyclic homology. Well, I'll have to explain precisely what's going on, and then to invertible numbers. It's this composition, which is very well defined under some conditions. And conditions are as follows. So one assumes that one has a, well, n summable, n plus 1 summable Fredholm module. Which means the following. We have our algebra. We have its representation as an algebra on some Hilbert space H. So pi is a homomorphism from A to bounded operators on H. And we have an operator F. So pi A to bounded operators on H. F is a bounded operator. And for our purposes, just F squared equals 1. This n plus 1 summable, it really means that expression from pi AF sit in L n plus 1 of H for every A in A. This means the n plus first power is trace class. Okay? So given such n plus 1 summable module, one defines a cyclical cycle A0, A1, AN. I will forget pi, just make life easier. So trace A0, F, A1, F, AN. Just one comment. So if you look carefully, I need n plus 1 of these things to get something trace class. Except that because F squared is 1, this is actually trace class. So this expression, you can rewrite as something in L1. So this expression makes sense, and this gives this map. Now, this makes sense. Now, if I want to map on on algebraic K-theory, this is really defined on the relative K-theory. So going via Fredholm module, I can get to algebraic K-theory at the cost of dividing out scalars. So I end up in the multiplicative group. So it's really kind of C modulo pi n, I pi n z. B is invertible C, copy of C. So, one comment, there are lots and lots of these Fredholm, Samogu Fredholm modules, depending on dimensions. So if I've got synth in them, yeah. Sorry? Yes.
By integers, not by constants.
No, integers.
No, but in a relative case of A to scalar, by scalars you mean integers in A.
No, not in A.
Complex.
No, it's complex. No. So basically what's happening is, so this is part of this log exact sequence involving relative and that one. And the Chen character kills the image of topological K-theory in the relative K-theory. Okay, so you get this one. So it's not automatic, okay, but it doesn't take much to get this one. Now once I got these pictures, well, there is another Chen character. It's kind of map to Karoubi-Villencourt K-theory, which is basically a map from here to homology of GL infinity of A, quotients in Z. Okay. Well, the obvious question is, does this map factor via homology? So that's general question. And it's, okay, there's one more statement. So this is somehow computable. As you can see, you can write down formulas. And you can compute things. This involves index of certain operators, things like this. This is somehow going via homology of some infinite group, where GL infinity A is thought of as a discrete group. These are non-trivial things. Okay, so it makes a lot of sense to be able to identify these things. Well, subject of this talk is really to try to find out how to construct cocycles on the group homology, so group cocycles. So let me start immediately with the first one. So group cocycles. Kind of general statement theorem which doesn't seem to appear anywhere, but which is used in certain cases. So suppose I've got a group, and I have some n category. I'll give you examples. Okay, and suppose that group X is automorphism of this n categories. So this is strict action. So, n category is a category plus two morphisms plus three morphisms and so on and so on. You get some examples. So I will assume, so one I've got this strict action. Another one, I won't write it, but I'll assume that these categories are linear for some commutative ring R. And so n category has objects, one morphisms, two morphisms, and so on, up to n morphisms. Okay, so I will assume that between n and 2, so there exists an invertible element, invertible k morphism for n and 2 k minus 1 morphisms. So any two objects that can be connected will be connected. And I will also assume that it's in categories, so automorphisms of any phi n minus 1 morphism. Well, this is canonical identified with my units of my ring. So it's, everything is over R. No, okay. No, for every k. For every k. So, given this, then, I don't know, call it theorem, proposition. Somehow, in low dimension, a lot of people write these things. It's true in general. So there exists a n+1 group cocycle by, well, C, Hn+1 G with coefficients R star. Well, could be a trivial one. It's not a trivial one, so this, I'll give you examples, but this cocycle is in some sense abstraction of extending the group action to higher skeleton of the classifying space of the category. R is commutative ring.
So just R star.
In the units.
Any evident group in a sense, yeah?
Yes. Well, for me it will be. Okay. That's where I will end up anyway. That's what I'm interested in. So, examples. One-dimensional case. So suppose that G acts on the category C, C is a category. So what we do is following. So pick up an object, okay, single object, and then for every group element, we will pick up alpha G, which is a morphism from X to GX. No, acts. Sorry, acts. Okay. G acts on C. What should I run? Out? Over? Yeah, okay, yes, I can do that. Yeah. It's a bit difficult to do tech, right? Sorry? No, acts, so objects to objects, and it's a X by functors. Right? A map from group to functors, and from category to itself, and preserving product. That's all. Okay? So by assumption, given energy, there is an invertible element here. Pick up one. Okay? And now let's suppose I've got two group elements, G and H. G. And let's try to draw a diagram. So we start with X, GX. Now I always mess up, mix up G's and H's. So GX and say GHX. Okay. So I've got these three objects. Now, given G, we picked up a one morphism alpha G. Well, given GH, as I'm going to do, right, we picked up alpha GH. Okay. Now, well, we picked up an object, a morphism from X to HX. Okay. GX as functors, so I get canonically alpha HX. I've got a nice diagram. Now, if we just follow it in the circle, we end up with a morphism of X to itself. Well, more, yeah. Right? Yeah. So automatically it's a billion group. Well, so I've got an invertible element. Right, so this composition produces C of GH, okay, in R star, so invertible element. And you check by hand that this is a group to cocycle. I think before, yeah, let's Okay, let's give an example of this construction, which will relate to that one as well. So this is this kind of one-dimensional situation. We get element in H2. So n equals 1. Right, so I need a, well, two-summable Fredholm module. I will forget about Fredholm modules in a minute, once I finish this example, because things become more interesting. But what will we do? Suppose I've got H as a Hilbert space. Well, polarized, meaning I've got a closed subspace there is a projection, so P is a bounded map from H in H, P squared equals P, image of P equals H plus. It does not have to be orthogonal projection. Just a bounded projection onto H plus, onto this closed subspace. I will assume that both H plus and its complement are infinite dimensional. It's not interesting otherwise. Okay? So let's try to do the category. Category will be the following one. Objects of C is, will be set of bounded operators, so invertible operators on H, which commute with P up to element in L2. So square integrable commutators with P. Algebra would be just linear span of this U in, well, this is a well-known group. This is actually a group, and it's called the general linear restricted group of H, of this polarization. Restricted of H. So this does get into the group, and we just take the group algebra here. So maybe I should write it this way. Okay. So these are objects, morphisms. So morphism will be as follows. So given the pair of elements in my G, well, the group obviously it acts on itself by multiplication, by left multiplication. So my G acts on objects. Okay. Now morphisms. So given two elements of G, morphisms from U to V will be as follows. So I have my idempotent P. I can, well, conjugate it by U. I can also conjugate it by V and take the product. Now, you can just think of it as an operator from a range of UP, U inverse to range of V inverse, to be consistent. So V, P, V inverse. Okay. Now, since they differ from P by something in L2, so this thing differs from P squared, which is P, by something, well, as a matter of fact in L1, but it's a different story, by something compact. So this is a Fredholm operator. Right? It's Fredholm. Well, given Fredholm operator, there's this notion of determinant. There is, of course, notion of index of Fredholm operator, but we are more interested in the notion of determinant here. So given such a Fredholm operator T, let's just define, this will be determinant of this operator, where determinant of Fredholm operator, by definition, is following. We look at the kernel of operator, its top exterior power. We look at its co-kernel, again, top exterior power, take dual. Now, since these are finite-dimensional vector spaces, these top exterior powers make sense. These are just one-dimensional complex vector spaces, and just take tensor product. Okay? So determinant of such an operator is just one-dimensional complex vector space. So complex line. Well, it sits in what's known as Picard category, but it doesn't matter. It is just a complex line. Okay? So morphisms between two objects are given by this complex line. No, it's linear. Automorphisms of an object, right? So, note, if U equals V.
No, it's a set, yeah. Morphisms is a set.
So, yeah. No, it's just it's one-dimensional vector space, but it's a set. So, well, there's one thing which is now. No, we are still on the level of one. No, we don't get two morphisms now. This will be the next example. It's the first example. I just want to see what's happening in this example. N equals 1. I get two cocycles. One category, right? No, just that one. Okay, there's one thing, so this is straightforward, so automorphisms of an object is a complex line. The one thing I need is composition, right? So let's go with U, P, inverse PU, just the notation. And the important part, of course, in categories, there is this composition. Morphisms UV cross morphisms VW to morphisms UW. Okay? So let's see what's happening. Now, my morphisms here are just elements of one-dimensional vector space. And I need some canonical map from here to here so that the composition will be associative. In that category, composition is associative. So what we'll do is the following. No, that's a bit too high for me. Well, so what's here? Here I've got determinant of P, V, PU, this product. Here I've got determinant of P, U, P, W. And then tensor product. So complex line, I get tensor product of these complex lines. Well, there's one thing we can do immediately. So determinant of, so tensor product of determinants of two Fredholm operators is canonically isomorphic to determinant of composition. Okay, so there's this, since I will quote it again, let me write it here. So determinant S, tensor determinant T is canonical isomorphic to determinant ST. It's just like index but multiplicative. And isomorphism is canonical. Okay? So this is canonical isomorphic to determinant of the product. This one, this is an idempotent, so I get PU, PW. Okay. Now, the next fact I need about determinants, so which is non-trivial this time. So this is kind of canonical, and if you sit down and think about it, you find out how it works easily. But the next fact is somewhat more interesting. It's due to Kari and Pincus, and which is the following. Suppose that S, I've got two Fredholm operators, such that differences in L1. trace class. Then there exists a canonical isomorphism from determinant of S to determinant of T. Canonical in the sense that it is, it's transitive. So if you have three of these operators, then determinant of one to the second to the third is the same as from determinant of one to the third. So it's transitive and determinant. And the map you get here, if you replace T, S by T and T by S, so if you flip them, the corresponding map is inverse to the previous one. You have to think a second what it means. This is a one-dimensional vector space, and this is a one-dimensional vector space. Okay? So this is an isomorphism from C to C. Okay? It's one-dimensional vector space, not the same as C. Okay? But think of it this way. So there's this canonical isomorphism which behaves as nicely as possible. Here, we have here. Now, the difference between that and PV times PW is actually of trace class. So there's this canonical isomorphism to determinant of PV, PW. It's actually an exercise to check that the difference between this operator and this operator is trace class. It does involve, our assumption was that commutator of U and P was L2. So the difference actually does involve product of two such commutators. Okay? Doesn't on the face of it. But if you use the fact that P is idempotent, it does. So the difference between those two is trace class. So it is canonical isomorphism here. And that's our composition of morphisms. So now I got a composition of morphisms. Now I've got my category. Now I've got my two-cocycle, right? So n equals 1. I've got two-cocycle. Let me write here. This corresponding C is two-cocycle on GL restricted H, coefficients, inverted numbers. Okay? Two-cocycle, central two-cocycle, this is just a central extension of a group, right? So this is the standard central extension of GL restricted H. So that's the central extension that shows up for loop groups, for example, right? It plays, I guess, pretty important role in conformal field theory. Sorry?
It's supper school is also important for this cover.
Yeah, that's the same, right? That's one thing. Also, the other thing, there was this K-theory thing I started with, right? So, it's K2 algebraic of this algebra, I wrote A, right? So linearly spanned by this GL restricted. So there's a map to H2, A, Z. If I use this cocycle, I ended up here. On the other hand, Fredholm module, as I said, I didn't say anything, but I can think of Fredholm module here, which is given by F equals 2P minus 1. Okay, that's an F square equals 1. It's bounded, F square equals 1. It's commutators with elements of my algebra are L2, so it's two-summable. So I get this Chern character, this map from K2 algebraic here. Yes.
Which take complex coefficients, like integer coefficients.
If I can, but it
No,
goes.
no, then it doesn't go really well to C star because
You take exponentials. No. You do get, well, okay, example, right? It's not so much example. So this algebra, what does it contain? For example, let's do an example, so maybe this will explain something there, right? So H is L2 of a unit circle, okay? H plus is, well, Hardy space. So functions with only positive frequencies in Fourier series. Okay. Projection P is just Tepe's projection. Okay. A contains smooth functions on the unit torus, in particular. So smooth functions. So any invertible smooth function actually sits in GL restricted. So in particular, the smooth functions here. So I get an element map on or functional on K2 algebraic of smooth functions on the unit torus in circle. Okay. In particular, well, it's computable. If I pick up two of such functions, well, suppose they extend to meromorphic functions in the interior. Okay, they just have to be invertible here. Then, well, each one defines a class in K1, so I have a product in K2. So I've got a class in K2 associated to those two functions. I get a number, what? C, U, V, invertible number. That's tape time symbol of these two.
yeah, but it's deep to consider group ring with complex coefficients. You get two cocycles of a group with coefficients C star.
No. I'm talking about this one's defined on algebra.
No.
Right? So, no, this one I don't need, right? Yeah, sure. H2GL, right? It should be the group here, right? Yeah, it's GLA. Yeah, the group, right? That's the group, right? The algebra is one thing, the group is the other one, right? So, and that's computable, actually. So in the case when these functions U and V are really have meromorphic extension to the interior of a unit disk, you have these formulas via basically based on character and such. So good. So that's so far so good. So that's this one-dimensional situation. So n equals 1. So let's go to n equals 2. And let's forget this two Somabu or Sanabu. So I'm going to replace one idempotent by 2. Okay? So, by the way, a bit similar construction is in Frankel and Zhou, except they work with formal loops. So it's not quite the same algebras. So you can adjust it to imply, well, formal loops will be a special case infinite of this. Okay? So I wanted two categories. So we start with P and Q idempotents. In bounded operators with some T-X Hilbert space. Okay? And G, certain subgroup of G and H. So, sorry, no. But they do satisfy some properties, right? Yeah, sure. So first one, PQ is an L2 of H. So the commutator is co-integrable. But no, there's no reason why you should compute. G is subgroup of GLH such that the following holds. It's actually two conditions. So first one, U inverse VQ, V inverse is an L2 for every U and V and G. And the other condition is, well, if I take P commutator PU times commutator Q and V, then again I am an L2 for every pair U and V in G. Okay? Well, I did say A group because these two conditions are not preserved under products. Okay? So there are lots of groups which satisfy these conditions. So pairs P and Q and groups, but there doesn't seem to be any universal one. In distinction to this GL restricted that we were working with in dimension 1 lower. But of course, example is, well, to answer the question, take T2 here. Then the two P and Q will be projections on functions which are only hardly in first or second variable. Okay. And my algebra spanned by group elements will contain smooth functions on the two torus. Okay. So smooth version of double loop. So double loop space. So in particular, once I'm finished, I will have a cocycle on double loop group. So smooth double loop group, not the formal one. So, given this background data, I want to construct a two-category with action of a group. So, well, for the guys who do not know what two-category is, so it has objects. It has objects. These will be things of a form Q, let's say. So call it QU. Okay. So for each element of a group, I will have an object, QU, which then to this one I will reassociate an idempotent. It has morphisms. I have one morphisms. So between two objects, QU, QV, we'll have to say what they are. Okay? And it has two morphisms. So between two one morphisms, well, I have these two morphisms. And, well, the obvious thing should be satisfied. So, of course, morphisms should be composed as normal morphisms are composed. So I have a associated composition of morphisms. And I have two compositions of two morphisms. So think of it this way. So good picture is this one, right? So two objects, two one morphisms, and a two morphism. From one morphism to one morphism. And then, of course, there are these compositions. If I've got other two things, then I can compose these two arrows. I can compose these two arrows, and then I get composition of these two arrows. And then vertical composition, these two arrows produce an arrow from here to here. Okay, so let's say two categories. There are lots of examples of such things in life. Except that now I have to produce it. Yeah. So before I do anything, let me somehow explain, I guess, why. So what's the idea? So in the case of this one category I got from for GL restricted, what I did was to take two of such objects, QU, QV, okay, and my one morphisms was given by the determinant of a product. Now I'm going to do things differently. I have a product of two such things, but it's not Fredholm. Okay? It has no determinant. Okay? So I would rather think of it as some kind of class in K0 of some nebulous algebra, which is not a certain ideal of bounded operators. Okay. Then, I have this. So this doesn't produce anything Fredholm, but the product of those two produces something Fredholm. Okay. So then I will think of a product of P, G, PH. Well, the PG is just G, PG inverse. PH is H, PH inverse. Okay. I would think of it as some kind of element K0 beside E. All of it is kind of as a philosophy. Well, I've got something in K theory, I've got something in K homology. I can do that one. Right? So pairing, think of it as a class, right? But pairing between K theory and K homology, really what it does is it produces, first of all, Fredholm operator, and then we take its index. So I'll write down Fredholm operator, and we'll take determinant instead of index. Okay? So I've got two stages. I have to have these one morphisms and then two morphisms. So two morphisms will come from that. Okay? So that's the idea. Except, of course, we have to be very, very careful because that doesn't mean very much. If it's all of it is defined up to a compact operator, all of it is defined as up to a index, invertible Fredholm operator. Right? So these are not quite good enough to define things. So let's try. Rather not try, but write down some definitions. I'll keep my notes, right? So 1 and 2, right? Yeah. Good. So objects are here. Just basically think of elements of a group. I wrote QU because these idempotents will show up in a minute, but these are just group elements. So one morphisms. Between U and V actually will be strings of elements of the form U, W1, WK, D, and group elements G1, G2, GK, GK plus 1. A set of such strings. GI, WJ, G. First forward. And the composition of one, so composition, well, same as concatenation of strings. I've got a string starting with U, ending with V, then another one starting with V, ending with Z. Let's put them together. Okay. So in principle, not much threatening. The interesting part becomes two morphisms. And so I have to work a bit. So I need to produce some kind of, first of all, Fredholm operator. On top of it has to have some nice properties. Remember, when we did the composition, the case n equal to 1, we had to know that there's some difference of trace class. We had to use that if I have a trace class perturbation of an operator, determinants are canonically isomorphic. Okay? So I have to be careful. So what I'll do is the following. First of all, we'll replace these by somewhat more clever projections. So given this U and V, write down, well, let's say F equals QU, QV plus U Q V inverse. And then corresponding G is U replaced with V. So it's still our product, Q and QV, except that I'm adding this extra term here. So the thing is Fredholm. Okay? By itself, it's not, but with this one. Actually, no, it's not even Fredholm, sorry. But the thing is, looks like invertible. So these are basically supported on Q. I'm adding something supported on 1 minus Q. Okay? And so the next thing we'll say, write E. Well, next, I'll write one of them. So an explicit projection which reproduces index class of F in algebraic theory, so in algebraic terms. So I think it's the only formula I will write. So 2 minus Fg times, I think Fg, right? Fg 1 minus Fg 2 minus GF 2 minus, sorry, FGF FGF. Next one is G 1 minus Fg, and the last one is 1 minus GF square. That's one. Well, it's a class corresponding to graph of F. No, no, we forgot Fredholm thing now. There are no Fredholms. It has nothing to do with P. Just family of operators. It has nothing to do with P still, right? And, well, 0 is 1, 0, 0, 0. Okay? So basically this replaces E minus E0, well, replaces this class QU minus QV. Okay? Except it has this very nice property that E minus E0 was actually contained in the ideal generated by 1 minus GF square. So it's really contained in the ideal generated by double commutators. So products like this. Let's say U prime, V prime, U prime, V prime, inside G. Okay. If you write down the difference E minus E0, you will find out that each term contains this kind of product. Okay. So the point here is, of course, that if I want something trace class at one moment, then I need a product of two such things and two such things. Okay, because otherwise I'm just not. Good. Now I wanted to write down these two morphisms. So suppose first we have two objects and two one morphisms. So the simplest one, G and H. Okay, but the simplest case of two one morphism. There's one morphism from U to V given by G, and there is one morphism from U to V given by H. Okay. In general, it's a chain. No, no, at the moment I've got chains of length 1, right? Afterwards we deal with longer chains. This is actually the place where things happen, right? In general, morphisms are chains. Start with chain of length 1. Good. Want to write something. I don't think I want to write the precise formulas, but so what you really do is now you will think about P, G, pH. I said we will really think of it as some kind of the product there as some kind of K-homology class, and couple it to this one. So up to not really very important things. I can write E0, PG, pH, pH, PG, E0. This would be a Fredholm operator. It's slightly, the formulas are slightly more complicated, but no point of really writing them. This would be a Fredholm operator. You can take determinant of that one. So that's a Fredholm operator, that's determinant. So it's a complex line, right? And this will equal to two morphisms between these. Yes. Yeah, so it's 4 by 4 matrices. So these are 2 by 2, 2 by 2. You just double those. Double those, right? So PG replace PG by PG, PG. Okay, yeah. You double those. Yes. It's simply because we have to do those here. Okay. From G to H. Okay. Actually, it's E0. Now, composition. So remember, there are two kinds of compositions of two morphisms that I need. Right. So there's one composition which is that one. Okay. So one composition is two morphisms still U to V, H, K. Okay. So I have to go to two morphisms U, E, G, K. Okay. And this really consists, so if you are somewhat more careful when I am here writing this one, you really compose you expand these operators. So one involves GH, the other one involves H and K. So so these are 2 by 2 matrices, 2 by 2 matrices, so 4 by 4 matrices. You go to 6 by 6 matrices and compose. And you can ship them relative to each other. No. But I'm composing things. I'm really composing things, right? In this direction, I'm really composing. In the other direction, not much happens. Well, I have to deal with these strings, but otherwise not much happens. In this direction, composition happens. I'm really composing this PHPG, PGPH, PHPK, and removing PH from the middle, so I get, it was GH, yeah, so I get G and K. Okay? And if I'm careful, I can still use this perturbation isomorphism here. Canonical perturbation isomorphism. Okay? So, perturbation isomorphism. works. So that's my vertical composition. Of course, only for things of length 1, strings of length 1. So what you do in general is it's a bit of a straightforward. So suppose I've got 2 strings. So U, G1, V1, G2, V2, GK, VK, W, and another one, U, S1, P, T1, S, L, TL, W. Okay, so I have to be able to do things for strings with different length. Okay, so actually what you do is fairly simple. So you take all these vertices here and cut S1 with these vertices. So the bottom one becomes U, S1, V1, S1, V2, S1, VK, and then we continue S1, T1, S, L, VL, TL, sorry, TL, and then W, the one, whatever it is here. Only the first one. And I just repeat this S. Okay? Here I cut the last one. So I cut this one and repeat this GK plus 1 here. Right? So I cut this one into pieces and insert all these T's here. They have the same length, they have the same vertices. Okay? So the only difference will be, so for example, here I start with those two. Okay, now I've got UV1, UV1, G1 is 1. I know how to compute, I know what these morphisms are. Okay? So this becomes like, looks like this. The other one looks like U, G1, V1, G2, V2. Last one is GK, VK, and then I get GK plus 1, T1, GK plus 1, T, what was it, L, W. Okay? And then I compute the determinant for each pair and take tensor product of those. Okay, so that for each pair, I have this determinant here that I can compute. Right, so E's only depend on the endpoints, which are the same as they should be, and the P, the thing in the middle, only depends on both. Okay. Take tensor products. And it works, meaning if I do something like this, T, S, S, then result, I can compute the determinant of corresponding determinant just forgetting what's in the middle. Okay? You have to check it, but there's this canonical isomorphism, which allows me to remove whatever's in the middle. Okay? So this is a well-defined vertical composition. Horizontal composition is stupid. You just tensor the lines. Okay, tensor this line with this line, and so on. Okay. And it does produce a two-category. Point number 1. Once I've got this two-category, there is obvious action on my group on this two-category. Okay, because the action is just by multiplying from the left by group elements. Okay, so remember, everything is numbered by group elements. And I can multiply group elements from the left, and things become consistent. Okay, so for example, here what I get, group element acting will just conjugate this expression. But I can compute what's happening on the determinant. So I've got action on my group on these two categories. And as I said, it produced, once I got this picture, I can produce a three-cocycle on the group. So G acting on two categories. And I had all these conditions. I will drop a picture. I will not write on the cocycle. Okay? So again, we do the same thing as before. Gx, G1x, G1, G2x, G1, G2, G3x. And then there are, once we chose for each G, we chose a one morphism from X to G1X. Okay, so we get all these arrows. Now, here I have to make another choice. So given such a diagram, X, G1X, G1, G2X of arrows, well, I can, by assumption, I can choose an invertible two morphism from here to the composition. Okay, that was these are one morphism. There's always an invertible two morphism. So we pick up an invertible two morphism for each of the faces, and then compose around an edge. Okay, so start with an edge, spread it this way, then I can spread it this way and then come back here. Okay? And thus produce a three-cocycle. Yeah.
You have, for example, now two functions on two-dimensional models here. Very simply functions are exponent, these small binding numbers, functions are exponent of functions. It will be integral of f0 times df1 times df2.
Yes. 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 So example. So okay. So apropos comment, what I do here in this case is non-trivial. Okay. There's one computation. As you were saying, my H is L2 over 2 torus. A P and Q are these projections onto functions holomorphic in one and other variable, okay? And I'll take Z1, Z2, and lambda, the two coordinate functions, and constant lambda. C of that is lambda. Okay? So of course, these are invertible functions on two torus, and lambda, well, lambda different from 0. Okay? So this is non-trivial. We did not finish, but it looks precisely like you get this Billings on. Yeah, precisely. Okay. But it's a three-cocycle on C infinite over 2 torus in the invertible functions. Okay. Not just on formal double loops, but on smooth loops. So in particular, you get three-cocycle on smooth double loops, double loop groups, as an example. Some comments. 5 minutes. So there's a lot of questions. Okay. So the first obvious question is, so first one, the one-dimensional situation was really associated to a square summable Fredholm module, which is the same as polarized Hilbert space. Okay, so the easy one. Is the Fredholm module, is there three-summable Fredholm module behind. Okay. Behind this picture. It's not obvious. So for tutoras, for example, obviously there is a three-summable Fredholm module. It's two-dimensional compact manifold. There are actually two of them. Okay? Whereas it's the K-homology we are talking about. Since this is two-dimensional, K-homology can be represented by three-summable things. Okay? It's not, so I can write, so basically this would mean Dirac operator in the tutoras. There is somehow, it's not quite obvious how to go from Dirac operator to these two projections onto functions holomorphic in one and the other variable. Okay? So, number two, something that, well, at least we believe it's true, but we didn't do it. So, point is as follows. Well, in particular, I get a cocycle on this thing. Okay. Well, I can always map smooth functions on the two-sphere to smooth functions on the two torus. Just pick up. Here's my two torus. Pick up functions which vanish. Well, smooth functions on, let's say, R2. R2 vanishing at infinity. So here's your copy of R2. Okay? So in particular, I get a, well, pose at the unit. So I've got a unital algebra. Okay. So I get a three-cocycle on such embedded copy of R2 to torus. Now, gluing. Can one glue these two three-cocycles? I think one can, but we did not do it. Well, once you can do it, if yes, you get this. You get H3 GLA, where what infinity A, where A are smooth functions of on any two-dimensional compact surface. Okay. So I think this would be quite interesting to get that one. Okay. So in particular, you get so this one example, this one-dimensional example, really talks about central extensions of a loop group, right? So one-dimensional case. We talk about, well, smooth functions to some, say, compact group, compact Lie group. We're talking about central extensions of this one, right? So we are looking at things in H2, L, K coefficients. Well, let's say do this one here. Well, if this works as it should, then we get kind of surface groups, right? Not loop groups anymore, but surface groups. I don't know how to call it. And you get a H3 class. They should be here, yes. Something should be here, yeah. But so there are some, well, I don't know. Yeah. Okay. So please tell afterwards. Yeah. Yeah, those gauge groups, yes. And yeah, which so H. Okay, this would fit. Thank you very much. And well, the last statement, the actual observation. Nobody says that these are supposed to be compacted algebras. Okay. So instead of looking at smooth functional and two torus, you can actually look at invertible elements in the irrational torus. rational non-contradictories. Still fits the scheme. Okay? So you get H3 classes for invariants of K3, actually, algebraic K3 for, say, non-contradictorial, for example. So it works for, so T2 theta. This is fine. It works in this case as well, for theta irrational. I think I'll stop.